Okay, let's get started. Hello, everyone. Welcome to the second day of the workshop on resource allocation. We have three amazing speakers. And the first one is Anupam Gupta from NYU. Anupam is an expert on many aspects of algorithm design, in particular online algorithms. And today we'll hear about robust online allocation.
Good. Thanks, Sahil. Thanks, Andres. Thanks, everybody, for coming. So I'll talk about this work that it's a couple of works, but also generally giving an idea of the kind of work people have been doing. And there's lots of open directions, so hopefully it'll be useful. Yeah, do ask if there are any questions and stuff. Okay, so very often I think of, so I work on both online algorithms and kind of robust optimization, and I think of this as a trade-off between robustness and efficiency. It is very loose, very broad strokes, but here it is. Robustness is worst case. We love worst case because it's so robust. We don't have to make any assumptions whatsoever. We design an algorithm, we look at the worst case, we know exactly. Most of the time. But very often it's considered pessimistic, right? I mean, how do you know that you're going to get the worst case? Maybe on my instances are nice. I should do better than the worst. So what we do is we define a data model very often. This is not the only way, but here's one way to do it. We define a data model and then we give algorithm for data from them. So you guys have already seen yesterday. We choose the data model carefully. And very often the data model is striking some balance between reasonableness. It shouldn't be a completely crazy data model, but for which we can actually give good output. Now often we get strong results. So efficient output. By efficient, I don't mean efficient in polytime efficient. Efficient in we are getting a lot of value out of this model, but often it's too stylized, too optimistic. And naturally there's a trade-off between these two things. There's the sort of point I want to make. So we can talk about various points on this sort of trade-off. And the point I want to make is that very often the algorithms that we give here are very different from the others. And in fact, it's not even clear that the algorithms we give here would work if we were on this point of this, whatever that point might be. So this is what today's talk is going to be. I want to be robust. I want to design algorithms which in some data model, but I want to be robust to the vagaries of that. Let's see what we can get. We want to get the best of both worlds. It would be great to get algorithms which are great in the stochastic case, and the same algorithm is great in the world. And in fact, it shouldn't even need to know where it is. It should be great for all cases in the middle. You can't have it, or at least maybe you can't. Okay, so just a recap in case you weren't here yesterday. I'm going to look at packet problems online. So there are 10 unknown adversarial values, V1 through Vn. V1 will always be the largest. I want to pick large values. These are values. They are in some order, and whenever I see an item, I need to pick. Now, if I see the item V5, of course, I don't see the fact that it's the fifth largest item, otherwise, it's boring. I see some value. I see 30 bucks. Should I take it or not? Maybe I don't. I see 100 bucks. Should I take it or not? Maybe I don't. Secretly, as sort of spectators, we know I made a mistake out there. And then items keep coming. At some point, I pick. I get some value. The best value was V1. I want to compare myself. That's pretty much the same. Let's say I want to maximize the probability of selecting. This is set critical. You saw this yesterday. Or I should say this is the ordinal secret. I could also ask for maximize the expected value of the element or the expected value of k elements in a. K could be 1. You tell me k, you can pick 10 items. Or I can have fancy things. I can have general packing elements. Columns come. Every time a column comes, it has a value. Think of the column as being, resource utilization. I'm using up so much of every report. I want to pack all the columns I choose into K, right? Where K is the amount of resource I have of each key. And to make this problem sort of interesting, to give a scale, I'm imagining that each resource utilization is between 0. So these are vectors between 0 and 1. I can pick some number, subject to these factors. So these are the kind of problems that we're interested in that you saw yesterday. Okay. Good. So what can we get? So in the adversarial setting, it's 4. And it's a situation like this. I'm going to give you one of these instances where I go up a hill and then I fall off. You really want to pick that item, but you don't know where the cliff is coming. So the best you can do is random. One of that. This needs to be formalized, but this is the main. So we assume random order, and in some sense it's necessary. And I'm preaching to the choir mostly out here. So I'll move on. I won't really spend too much. The stochastic setting, very easy. And I'm going to imagine that items, instead of imagining a random order of the item, I'm imagining that each item is arriving at an IID time between 0 and 1. And Jenkins algorithm still works for the second. You set a time limit of 1 over b. Then you sample items until time 1 over. You look at the largest value you've seen. Then this is the threshold. And you'll pick the first item in the second half, which is higher. We know that this is a 1 over e approximation, 1 over e competitive, whatever you want. Okay, good. For the k item case, you get many more tries, so you can do much better. So if k is large, you can get close to 1 minus epsilon. And this is tight as well. Bobby Wengler had this nice paper in Vancouver, 2005. So, and then you can extend it to LPs. It's almost the same kind of trade-off. It's just that log d comes in. The dependence in the dimension is logarithmic dimensions. And this is some nice paper, starting the work of Thomas Kessler, and actually even earlier, David and Hayes, and many others. Yeah, I'm just giving some paper. Anyway, the stochastic model, very well. Okay. So I want to understand, remember this line, worst case stochastic, worst case hopeless, stochastic pretty dark. Good. And so we're looking at these semi-random models. And what are these semi-random models? The input is first drawn from some data model, where the adversary can corrupt it in some form. And maybe, how about, don't worry too much about the causal order between these things. It's not necessary that, one happens before the other. There's some adversarial corruption, there's some stochastic part, and there's some combination. So here, technically, slightly off. But look at these lines. Here's what I want to do. There are G green items. These are good people, G for good. And they behave according to the model. They come at random times between the. But the adversary can inject R bad times. And these the adversary can choose. For our results, technically we need this choice of the adversary to be oblivious of this choice of the random. Think of the adversary as planning beforehand. It knows that the good people will come at random times. It sends the right people at specific times, like an injection attack. But it's not an adaptive injection. And the question we are asking is, well, can the right people mess things up back? Can it be the case that now we will do much worse on just the green items? I don't want to get value from the red items. These are bad people. I'm not counting on the increase in the value due to their value. I just want to compare myself from compare myself to the optimal for green. So maybe I should just be slightly careful out here. I was a little loose in my language out there. If I pick a red person, I will get there. I have a credit card, so that's okay. I can get there. But the yardstick, benchmark I'm comparing myself to is optimal green. So that's the difference.
So it doesn't make sense if you're trying to pick the maximum. That could have been red. This is the one for the objective value.
So I could look at so I won't compare myself to the max of all green plus red. I want to compare myself to the max green. But if I pick a red item which is much more than the green item, I'll still get the value. So, what can we hope? Can we hope to get the max green item? Or can we hope to get somebody who's at least as good as the max green item with high probability?
You know RNG in advance.
Let's say we know RNG, our algorithms will also work when you don't. And of course, I don't know whether an item is R or G, otherwise it's wrong. So consider this instance. It's a long sequence of red items which are increasing. And there's a single green item which is coming at a random time. Right? And suppose I'm not looking at the value version, I'm just looking at like the ordinal version. When an item comes, I just see whether it's bigger or smaller than the previous. In some sense, I want to maximize the probability of picking the best. So after this first three red items, I see a green. And it looks the same as the first four red. I don't know whether I've seen this or I've seen that. So having one random green item is not really helpful. So if I make no other assumptions, I can't do too much. So let me tell you assumptions that I can make under which I can say something. So here are two assumptions I will make. Or rather, two different assumptions I can make. I'll make either of them with the situation.
Does it make a difference if you see the value down on the ordinary information?
Good. So, yes, but I still don't know how to handle it in this case.
Yeah, in this case, I get.
Exactly. So here is in the value set, whenever I'm talking about value, I'll make this kind of assumption. I'll compare myself to the best set, but I'll make some assumption. I'll assume that I have some Polyane approximation. This is one kind of assumption I'll make, and I'll give some results. And this assumption will be useful when I'm picking many. The alternate assumption is look at the best set amongst the greens, which excludes one. Think of this as a multiplicative additive loss. It's like an additive loss of one item to figure out this. If this looks like a weird assumption, just ignore it. We'll come back. Right now, let's just assume the following. I'm going to give you a result which compares to the max set among the green items, but I have some good approximation. And here is what else. Let me here. So changing the slide a little bit. I've been changing the talks a little bit. It's not the smoothest. Sorry. So here's the result. First result I want to show you. Perhaps the only result, I don't know how much that is. I'll give you a constant approximation for pattern. The value of pattern. As long as the right hand sides are something like log. This should be compared to the previous results, where I was getting a 1 minus epsilon approximation, where the right hand sides were something like log divided by epsilon. I don't know how to get 1 minus epsilon results. I only know how to get. This is a result. This is a question that's still. If I make more and more assumptions, I can do something. So remember, a pattern field looks like this. Columns come online. Columns are between 0 and 1. And they must pack into k times. All one. We can extend this to profits. We can extend this under some further restrictions, but under the most general model. And then I can do something for single item settings, but now I can only compare myself to the second largest green. It's like this additive loss of 1 with some probability which is 1 over log. I don't know a low problem. I don't know a bad example showing that this is negative. All I can say is I can pick the second largest item or higher with probability 1 over log. The results are not tight, and definitely quantitative improvements are definitely very much on it. We tried at some point, we tried and we didn't have a sort of matching bounds from the other side. So help us. Okay. And then there's something for the value version of the single item, but let's not. Oh, by the way, this was a paper with CJR, Mark Molinaro, and Sahil. And this, there's some previous works as well. Okay, questions? Please.
Quick question.
Yeah.
So with these red items, it seems like the continuous time model and the discrete time model are no longer equivalent because like by continuous time kind of by time t you expect to see a t fraction of the green item. For discrete time you don't have such a
You don't have absolutely. So that's another excellent question. I don't know how to get our results in the sort of discrete time model in the random permutation. It's
A log star.
there is a log star out there. It's not just a plot on the morning. Yeah. It's good. Other questions? Yeah.
Do you consider like restricting just the fraction of the red item, like when it's like very tiny?
Good.
All the way to the constant fraction?
Good. So if the number of red items is very small, we have to make one more assumption that most of the value is not concentrated on a small number of columns. It's not like this, there's one element that you have to pick to get all the value, otherwise everything else is gone. So there's a single Rembrandt painting in this whole thing, and you pick it or not, then you kind of like a single item. Not great. So if you don't have that situation, then you can get it. So if there are few red items and the value is not too concentrated, you can get very good. Good. Okay, let's see how far we can get. I have a long list of things in the menu. Okay, so let's do the key item sector. It's simple. Hopefully, you give me an idea. The online allocation is essentially the same idea, a little more elbow grease, and this one you see. Okay. So key item sector. Remember, green items, red items. This is actually starting from an older paper with Sahil and Goran and Domagoj, but the red items are chosen adversarially, the green items come in. We don't see the colors, of course. We want to do that. And we want value which is comparable to the top k green items. And we have an estimate, poly estimate of pop. So let's see what algorithms we might use. So first, let's just go back to our standard algorithm without corruptions. So if k were 1, essentially we were setting some threshold, and then we were picking items which were bigger than that. We would pick this. First item bigger than that. And of course, you can see that I can mess it up completely. I'll give one massive red item, so my threshold is going to be like zillion. And then you won't pick it. Of course, there's broken algorithm, but this is just showing that the algorithm is not robust. Okay. So what are we going to show? We're going to show that if we are allowed to pick a large enough number of items, then we get a constant fraction of pop, assuming we have an estimate of pop to within. Even for higher dimensions. So this was the main theorem. So let me give you the idea. So the idea is going to be, the algorithm is very simple. The first is I'm going to give you a robust, what I call a single parameter. There's a magic number. There's a little bird came and told me this magic number. I can get a very good one. And then the second thing is, well, I don't know this magic number, but I'm going to learn it in an online system. So this is going to be this two-part algorithm. And the second part, whenever you see learn, my favorite algorithm, the expert's algorithm, I'm going to use that. But which single parameter? That's the real question. So here is the, So what do I want to do? I want to imagine an algorithm with a single number. And single is not important, but in this case, a single number. If you told me this single number, I'd have an excellent. So here's one algorithm. Suppose the green values were G1 through Gn. What do I want to pick? I want to pick k items. Right? So I want to pick items G1 through Gk. If you told me Gk, you told me the value Gk, I would pick all items G1 through Gn. Great algorithm. Single parameter. Okay. Is this algorithm robust? No. Robust to what? Robust to adding red items. And the problem is that imagine a situation where G1 through Gk minus 1 were all huge, but Gk was like. So the threshold is 1. What I can do is I can inject a lot of elements of value 1. So what are you going to do? You might end up picking all the 1 items. You'll get k, whereas you should have really got about km. So not robust to injection. So here's a different algorithm. Pick items above threshold opt over 2, over half the array. Okay. So if I pick k items, I'll pick, opt over 2s. But maybe, picking just items opt over 2k is not picking all of them. Go back to the sort of previous example. There might be, how do I know that there is a good solution whose values are above all? Right? I need to show you that there is a good solution that I'm sharing. Well, it's not too bad. So here is the simple thing. Take the optimal solution and drop all items which are below this threshold. How many items can you drop? At most k. Each item that you're dropping has value less than opt over 2k. How much value have you lost at most opt? So you started with opt, you throw away some number of items, you throw away at most opt over 2 of value, you still have opt over. So there is a good solution, all of whose elements are bigger than opt over. And any solution I pick will, can pick up to sort of k items of value at least opt over 2k. Yeah.
I guess sort of like now if you consider the adversary could also delete things to also versus.
If it starts deleting things, then it gets a little more complicated because then I have to worry, then I have to change my yards. Because it might delete the most valuable items. Absolutely. So here injection attacks on in this way, particular. Yeah. Good. Okay, how are we doing? Sorry. Good. Okay. So if I knew this threshold, I'd be in great. Of course, I don't know this threshold, but I've got done part 1 of my thing. There's 2 parts, so I'll do the second part. I've already told you what the second part is. It's this, it's the experts. So I learned this parameter robustly. Here's what I'm going to do. I'm going to break up time into chunks. Okay. I'm going to use the first chunk to estimate the value that each threshold will give. If I set the threshold here, how much value would I get? If I set the threshold here, how much value would I get? And so on. Based on that, I'll select the threshold for the next step and so on. So I'm using the expert type. So maybe let me. This is where I'm using the estimate of opt. I knew opt within poly n. Now threshold I can change to powers of 2 or powers of 1. So there are about log n guesses for what this threshold could be. I'm going to do experts to do almost as well as the best. What am I doing? I'm breaking this time between 0 and 1 into L chunks. I'm going to look at the first chunk. I mean, in each chunk, I can figure out how much value I would have got had I set the threshold to 1, 2, 4, 8, and so on. That gives me the reward for that threshold for that chunk. Then I'll go on to the next chunk, use expert to reweight things. And here I'm kind of assuming that you guys have seen the expert's algorithm. If not, catch me later, I'll tell you. It'll be the most useful thing you learn from that algorithm. So it's a black box application. And you'll get a payoff which is oftentimes the best choice in hindsight. Best choice in hindsight is giving for omega minus the regret. So maybe so even those who are in the audience, even experts, no pun intended. There's a slight subtlety, okay? And I'll tell you about this, and probably that might be the last. Okay. So I want to control the regret. How much? Okay. So the usual thing, this is a mouthful. The usual guarantee, I'm giving you black box guarantee. R stands for reward. RI stands for the reward of, so RI stands for the reward of expert. So this is all. This is the best expert in hindsight. This is my performance. Ignore what the notation is. Opt minus apple. Opt is more than apple. It's opt. And how much is it? This is the regret. The regret is epsilon times opt. Plus analytic term, log of the number of experts divided by epsilon times the scale of the problem. The maximum per step reward that an expert. Okay. This is your standard experts analysis that you will see in everything. Our problem is that different experts have different scales of reward. Some experts very large reward, some experts are tiny. Here's a better expert guarantee. This is called multi-scale experts. It says for every, my behavior, this is alpha. Its regret against expert I is epsilon times the reward of expert I plus the scale of expert I times log Q. And this is true for everywhere. So your algorithm is good against against an expert, against each expert, proportional to the reward of that expert and the scale. And this is good. It's a useful thing to know. This is a very nice paper. I should have put the reference. I'm sorry. The paper we discussed in Bubak, Nikhil Devanur, G. Guan, and I'm forgetting.
Ran
Nazar. Good. Okay. Useful. If you use this, I'm not going to bore you. It's early in the morning. For us, R right star. If I knew the right threshold, I would get omega. Okay. What's the amount of reward that expert I, this magical expert, will get in any one particular chunk? I broke into L chunks. Okay? I assumed there were a large number of items. So what I can make sure is that the amount that this expert wins in any one particular chunk is approximately octogonal. Just concentration. I have to do a little more tricks to, so cap values and stuff like that, details. If I'm getting opt overall and there are L chunks, then each chunk should get opt overall. And I have enough items so that I can get concentration. That's the meaning. And now if you sort of work the parameters out, our loss is N times the log of the number of experts. Number of experts is log N, so that's log N. We know this term. So it becomes opt over L. That's the scale of the problem. Times 12. You're balancing those two terms. As L gets large, the number of chunks gets large, you get very good value. But if L gets large, then you don't get concentration. So you got to balance these two things. Okay, details. Once you know the general idea, you'll be able to do this. So the main idea was step one single parameter algorithm. The little birdie told me something, I can do this. And secondly, you have times broken up into many little pieces. Use the feedback from the previous piece to update. You're just learning, online learning. And if you need to be careful, use multi-scale. That's it from me. This can give you the results for multiple items, even for higher dimensional problems. Oh, so maybe one last sentence about higher dimensional problems. Some of you were here for Sahil's talk yesterday. He talked about this table of this is online application. Ignore all this. He talked about and ignore all this thing. I'll tell you the important. He showed you an algorithm which is similar to this. Maybe it looks different, but it's called the Agrawal-Devamura. Beautiful. For online application, for these packing problems, even more. The important thing is this algorithm takes single parameter gamma. Gamma is like the conversion ratio between, I'm earning in dollars, but I'm using up resources in kilos. I need to translate between those two. Gamma is the conversion rate. If I know the right conversion rate, I can get very good. I don't know the right conversion rate, what should I do? Multi-level, multi-scaling. So that's the moral of the story. Same analysis. I mean, of course, why this algorithm is good, why Agrawal-Devamura is good, that's a different story. But that Sahil already good. Good. Okay. And I'm out of time. I'm not going to tell you the single secretary thing. You can catch me. But let me just go to the last slide. It is the last slide. So we call this the Byzantine secretary. You may not like the name. It's a semi-random, we were just talking about this. This is the Hoover contamination model. I'm taking a distribution, but I'm adding an epsilon fraction from another distribution, or in fact, from a worst case. And we saw one algorithm, two is I didn't have time for adversarial. And the important thing is not the results. The model is good, but what I would say is we should think of other models, ways to make our algorithms robust. This is not the only way that exists, but in general, would be great to have better time results, lower bounds, but also other models that interpolate. This best of both worlds. For bandits, actually, for those of you who have been following that, there's some very nice results. But they show algorithms which are good for stochastic bandits are also good for adversary. Here we are taking big hits. Sometimes small hits, but hits none. So we should figure out how to handle these things. And in general, whenever we design an algorithm for the stochastic setting, maybe it behooves us to ask the question, how beholden are we to this? What happens to the stochastic model? Not exactly what comes out. What if it's slightly off? Anyways, that's it. Thank you, guys.
We'll review in like 24 minutes.
Please take a seat. We're about to start our next talk. Next talk is by Víctor Verdugo. He's the assistant professor at the Universidad Católica in Chile. If you were here for tutorials, I promised he would talk about this demand problem. He will give the most recent picture on this problem. So thank you, Victor.
Thank you. Thanks a lot. And this thanks a lot, actually, for the invitation. Yeah, so as Andres just thought, I will tell you about some recent results that we did with Jose Soto, which is a professor at USAG, and also with Javier Marito, which Javier, but actually part of the work is the master thesis of Javier. It's excellent student. And he moved it to Maryland for a PhD. So I hope we will see him here. So, all right. So, well, let me start with a brief recap of the combinatorial allocation problem. So this is essentially what Andres showed yesterday. Let me briefly show it again. So I will have n agents, okay, and a set of items. Yeah, so that we call I with the set of items. And each agent will have a valuation function, Wj. And Wj will be defined over subsets of items. Okay? And it will take positive values. And the goal is to find the maximum welfare allocation of item bundles. So meaning I will pick subset of items, okay, and I will assign this subset of items to the agents in order to maximize the total weight. But I have one constraint, yeah, which is that they should be all disjoint. What does it mean? It means that I'm allocating only, so every item is allocated only once, right? So I cannot allocate an item more than once. Therefore, let me give you an example. So let's say that here I have 3 possible bundles, yeah, and 3 agents. And for the first agent, maybe the top selection is, I don't know, the bundle in blue, let's say, with a weight of 6. And then for agent 2 is the one in red with a weight of 8. And for agent 3, the one in green with a weight of 10. Yeah. So let's say that these are their most preferred bundles. Okay, if they have to choose, that would be the choice. Okay, but the problem here is that this is unfeasible, right? Because I'm allocating items more than once, right? So they intersect. So then this is not a feasible allocation. Okay, but on the other hand, this is a feasible allocation, right? Because here I have again these 3 bundles, right? So maybe the values are lower, right? And maybe actually every agent will be more than before, but now this is a feasible allocation. They do not intersect, right? I'm allocating every item at most once. Right? And possibly some items are not applicable. Like in principle, that's possible. And of course, as you can already see, the problem will be very hard, right? So we can encode hypergraph matchings by solving this problem. And now, as Andres said, for the rest of the talk, I will focus on this setting in which agents demand bundles of size at most k. So this is where they put all the value. Yeah? So essentially, they only care about selecting k items and not more. So how do we model this setting? Well, I will model this as an optimization problem over hypergraphs. So the nodes in my hypergraph are given by the set of items. Then each agent has a weight function over the set of hyper edges. So imagine that every hyper edge, now it's a possible bundle. Right? And they have size at most k.